Welcome to the Unit on Integration, Integrating Polynomials. The objectives for this session are to find y given dy dx for polynomials. Recall the rule for differentiating x to the power n. If y equals x to the power n, then dy dx equals n times x to the power n minus 1. The reverse of differentiating is integrating, and the rule for integrating x to the power n is if dy dx equals x to the power n, then y equals x to the power n plus 1 divided by n plus 1. Integration is the reverse of differentiation. So what do we do if we want to differentiate? We start with, say, x to the power n. We multiply by the power and then subtract 1 from the power to give n times x to the power n minus 1. And what do we do if we wish to integrate? We start with, say, x to the power n, then add 1 to the power, and then divide by the power, so that we are left with x to the power n plus 1 divided by n plus 1. X to the power n, or x to the power n plus 1 divided by n plus 1 is the function, and the gradient function is respectively either n times x to the power n minus 1 or x to the power n. Now, integration is the reverse of differentiation. Before we go into any more details, let's take a look at 3 more examples. Y equals x cubed plus 6, y equals x cubed, and y equals x cubed minus 1. All 3 functions are different. However, when we differentiate, we obtain dy dx equals 3x squared for each of them. So when differentiating, constant terms disappear. Functions which only differ by a constant differentiate to give the same function. Therefore, when we integrate, we must add a constant of integration at the end of a function. So when we integrate dy dx equals 3x squared, we obtain y equals x cubed plus c. And notice here we've added a constant of integration. So if f dash of x equals x to the power n, then f of x equals x to the power n plus 1 divided by n plus 1 plus c, where of course n does not equal minus 1. Let's take a look at integrating x to the minus 1. We cannot use this rule that we've indicated here if n equals minus 1, since 1 over n plus 1 is undefined at n equals minus 1, as we cannot divide by 0, as you can see from these formulae. We will look at how to integrate x to the minus 1 in a later session. Let's now take a look at some examples. Find y for the following. Part A, dy dx equals x to the power 6, and Part B, dy dx equals x to the power minus 3. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve example 1a first. The rule which we will be using has been highlighted. Since dy dx equals x to the power 6, when we apply this rule, we add 1 to the power and then divide by that new power. So we now have x to the power 6 plus 1 divided by 6 plus 1. And of course we must add the constant of integration, c. Here's the value n plus 1. And this becomes x to the power 7 divided by 7 plus c. Now let's solve part b. Again, we add 1 to the power and then divide by the new power. So here's n equals minus 3. So our new power is minus 3 plus 1. And this tidies up to x to the minus 2 divided by minus 2 plus c, which is of course equal to minus a half times x to the minus 2 plus c. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve example 2a first. Again, the rule which we are applying has been highlighted. So n plus 1 is a third plus 1. And tidying up gives us x to the power 4 over 3 divided by 4 over 3 plus c. And when we're dividing by a fraction, we multiply and flip the flat fraction over. So we're now left with f of x equals 3/4 x to the power 4 over 3 plus c. Now let's have a go at example 2b. F dash of x equals 5, and another way of expressing this is 5x to the power 0. So n equals 0, and therefore f of x equals 5 times x to the power 0 plus 1 plus c. Therefore, f of x equals 5x plus c. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. Before we begin, remember that when integrating polynomials, apply the rule for integration separately to each term. So, dy dx equals x to the 4 plus 3x squared minus 4x to the minus 3 over 2 implies y equals x to the 5 over 5 plus 3x cubed over 3 minus 1 minus 3 over 2 times 4 times x to the power minus 3 over 2 plus 1 plus c, which tidies to x to the 5 over 5 plus x cubed plus a half times x to the power minus a half plus c. Now let's take a look at indefinite integrals and some notation. The symbol in red, which looks like an S which has been stretched, represents the integration process. So integral f dash of x dx equals f of x plus c. So for example, the integral of x to the power n dx equals x to the power n plus 1 divided by n plus 1 plus c. So this elongated s means integrate. X to the n, in this example, is the expression which we need to integrate. And dx means integrate with respect to x. When integrating a polynomial, we can integrate terms one at a time. So integral of f of x plus g of x dx equals integral of f of x dx plus integral of g of x dx. Pause the video and have a go at example 4. Press play when you're ready to view the solutions. So let's solve example 4a first. We are required to integrate the expression shown on your screen. Let's solve this. We are going to integrate term by term. So the integral of x squared becomes x to the 2 plus 1 divided by 2 plus 1. And the integral of minus x to the power 2/3 becomes minus x to the power 2/3 plus 1 divided by 2/3 plus 1. And if we tidy up, we obtain x cubed over 3 minus x to the power 5 over 3 divided by 5 over 3 plus c. And tidying up some more, gives us x cubed over 3 minus 3/5 x to the power 5 over 3 plus c. And now for example 4b. Let's integrate this expression. Again, we're going to integrate term by term. So the integral of 3 becomes 3x, and the integral of x to the power minus a half becomes x to the minus a half plus 1 divided by minus a half plus 1, plus the constant of integration c, which equals 3x plus x to the half over half plus c. Which tidied up becomes 3x plus 2x to the power half plus c. Now let's have a go at another example. This integral can be expressed as shown. pt to the minus 3 integrated becomes pt to the minus 3 plus 1 all over minus 3 plus 1. And the constant q squared integrated with respect to t simply becomes q squared t. And tidying up, and finally tidying up some more gives us minus p over 2 t to the minus 2 plus q squared t plus the constant. And now for another example. Find the integral of 2x to the power 5 plus 3 with respect to x. So solving this gives us the integral of 2x to the power 5 is 2x to the power 5 plus 1 all over 5 plus 1, plus the integral of 3 with respect to x, which is 3x, plus the constant. And tidying up, and tidying up some more, gives us x to the power 6 divided by 3 plus 3x plus c. Now have a go at this example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve example 5a first. Find the integral shown on your screen. Let's solve this. This integral can be expressed as 3x to the minus 2 minus 4x to the minus a half. And integrating gives us 3x to the minus 2 plus 1 divided by minus 2 plus 1 minus 4x to the minus a half plus 1 divided by minus a half plus 1 plus the constant. And tidying up, and tidying up some more, gives us minus 3x to the minus 1 minus 8x to the half plus c. And now for example 5b. Find the integral shown on your screen. Let's solve this. First expand the brackets as shown, and then integrate. So integral of x squared dx becomes x to the 2 plus 1 divided by 2 plus 1, and integral of 3x to the minus 2 dx becomes 3x to the minus 2 plus 1 all over minus 2 plus 1, plus the constant of integration. And tidying up gives us x cubed over 3 plus 3x to the minus 1 over minus 1 plus c. And finally tidying up some more gives us x cubed over 3 minus 3x to the minus 1 plus c, as shown. And now for example 5c. Four x to the power 3 becomes 64x cubed. Splitting up the fraction, we have 3x to the half minus 3 plus x to the minus 3 dx. And so if we now integrate, we obtain 64x to the power 3 plus 1 over 3 plus 1 plus 3x to the minus 5 over 2 plus 1 over minus 5 over 2 plus 1 plus x to the minus 3 plus 1 over minus 3 plus 1 plus the constant of integration. And tidying up gives us 64x to the 4 over 4 minus 2/3 3x to the minus 3 over 2 minus a half x to the minus 2 plus c. This brings us to the end of this session. If you have understood its contents, you should be able to find y given dy dx for polynomials. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.